these functions of two variables. Just another kind of a half of the introduction into calculus of many variables. Okay, so once again, there could be there are two variables already as it is in calculus 1. Yet they still multiply, but they could multiply in two ways. Either the independent variables multiplies there two, or the dependent variable multiplies by 2. So parametric curves have two variables in the dependent variables. So another way to put it is you have two functions of the same variable. Or the input variables, the independent variables multiply, such as this. So that produces functions of two variables. So this is the illustration here. Parametric curves, one input, two outputs, or functions of two variables, two inputs, one output. Okay. So the calculus applies entirely. Certainly becomes way more complicated. But some things remain the same, and so, for example, the ability to find the rate of change of a function in a particular direction, so in this particular case we have two functions, and we can then think about it as if it is once again a surface or a terrain, and where the output of our function, say z, is in fact the elevation of that terrain, as it depends on the coordinate of that point on the map, x, y. Okay, so so then to find out the rate of change of the function with respect to in two particular directions, meaning along the x-axis or along the y-axis. So the x is still the same, so I could have x is here, y-axis there, and so so if I fix the value of y, what's going to happen? Any particular value of y I fix. This is what's going to happen. I will my terrain. Well, this is a particular value of x, y. So y fixed. Okay, what does it do to our terrain? First of all, it is as if I'm traveling in that particular direction. So I can travel in any direction I want on the terrain, but if I choose one direction in this time along the x-axis, then that's what happens. It means y is not changing, so no north-south motion. Okay, and then what has happened to terrain? Mathematically, you will end up with something like this. You cut out a piece of the terrain, like sometimes they do when they build roads, for example. They blow up. You drive, you can see a flat. You have the terrain. You see a mountain from a distance. So you get closer, you see that it's been cut through. So a flat vertical plane that is flat vertical plane, and the top of that plane is that the curve that we could think of as a function of one variable. So like this. So that top of the not top of the mountain, but just top of that flat cut. Okay, so the highest point could still be here somewhere. Okay, but the cut, and we are driving like this. Okay, that is as a result a function of one variable, and as a function of one variable, it is subject to all the methods of calculus 1, and we could then, for example, we can through differentiation find the rate of change of the function in that direction. So the function that we looked at yesterday was this, and so I differentiate the function with respect to x, meaning y is fixed, and so as you can see, using the Lagrange notation. I'm sorry, that is actually the Leibniz notation that I have here. Advantageous, instead of using the prime, becomes more important because now we have two variables. So you have to point out what variable you are dealing with. So I'm dealing with variable of x. Okay. So then it automatically it assumes that y is fixed, which means it's treated as if it is a constant. It is a constant. So when I get to differentiate this function by the chain rule, okay, I will have what I differentiate sine first. I have then cosine x plus y squared. Okay, so that part doesn't really involve anything new yet. And here I have to differentiate. This function, what's inside. Okay, so a two-step differentiation, as always, with the chain rule. And now I can see that I differentiate with respect to x. So I still have cosine x plus y squared. And what is the last term here? No, differentiate x. So I'm talking about this part. Differentiate x plus y squared with respect to x. Y as well as y squared is a constant. When you differentiate a constant, what do you get? 0. And when you differentiate x, you get 1. Right? So it is, in fact, 1. Okay? So once again, has nothing to do with implicit differentiation, related rates, all of that. When in calculus 1 you have x and y depends on x. Y does not depend on x anymore. Both of them are, look at it, it's right here, both of them are independent variables. That is literally the explanation of what's going on here. It is, they used to be, or y was dependent on x, calculus 1, and now both of them are independent, so as such, differentiation with respect to x does not affect y. Y is fixed, it's constant. So turns out to be equal to 1. And so that gives me the rate of change. Depending on the location, so location is x squared plus y squared. Location is x. So let me just explain what this is supposed to mean. So the slope at the point xy, maybe this point might be xy, over here, point xy. So we picked a location, and then we're interested in the slope, but not there are infinite many slopes. We're looking at one particular direction, and this in direction of the x-axis. Slope at xy along the x-axis. Okay, so that's what we have discovered here. So it does depend on both x and y. So it's like a lot of more going on. Not only there are more points to look at rather than a straight line in dimension 1, you have a whole plane, as well as at every point there are also at least two directions to worry about, in direction of x-axis or direction of y-axis. Okay, similarly we go with the other variable. So once again we differentiate by the chain rule. We still have cosine x plus y squared, df dy this time, x plus y squared. So now the attitude changes right away because now we are dealing with the same function, x plus y squared, while we're differentiating with respect to y, not x. So what's the answer? What's the answer? X fixed. So once again, x fixed, it does not vary. It means it's a constant. And it is a constant, derivative of a constant is 0, so what do I get? 2y. 2y. Okay, derivative of x is 0, derivative of y squared with respect to y is 2y. Sometimes you can literally carry out, take this far enough so that you don't have to worry about, so x kind of will go out of consideration. I could continue like this. Here I have df dy of y squared, and then there is, well, no doubt that this is 2y. Okay, so if you just realize that by you're applying the sum rule first, right, and then you realize the derivative of x with respect to y is 0. And then you're left with y squared. You differentiate y squared, you get 2y, and that's what this is. Okay, so anyway, all calculus applies. The skills of differentiation are still required just as well, except in dimension 2 you'll have to differentiate twice. There are 2 derivatives. If it is 3 functions of 3 variables, 3 derivatives to worry about, and so on and so on. So they're just more of the same, plus the complexity of the complexity that is still hidden, and that is, as I mentioned, certainly considering directions along the x-axis, and then in the direction of y-axis is fair, but on the other hand, you do not, there are what about diagonal direction. That is would deserve separate analysis, but we're not going to go in the direction. This is just an outline, an introduction into functions of several variables, to calculus of several variables. Okay, And then we might have some time at the end to look beyond this. But at this time, we'll just stop here. So it does test your understanding of a function of derivative or calculus of one variable in order to handle this. So just things certainly become more complicated. However, it is in fact the next topic is the most challenging in the course. Series. So there is no multiple dimensions to worry about. So that's the good news, but it's way more abstract, less visual, and that's why more challenging. So the theory is based on the theory of sequences that we took care of some time ago. So we'll review that a bit later. But first, let's see why we care and what is that we're trying to accomplish here. And so we'll start with a review of linear approximations. So remember linear approximations in Calculus 1? What's the idea of a linear approximation or linearization, any of that? What is it about? Nope, no recollection. Well, let's solve the problem then instead. So find square root of 4.1 without a calculator. Well, certainly you cannot really find it, but we're talking about the approximations. So what is the best bet on the value of 4.1, square root of 4.1? On the surface, we certainly can say something about this number. What can you say about this number?
Close to 4.
You mean 2? Yeah, close to 2 because 2 is the square root of 4. 4 is close to 4.1. Okay, so that's the idea, right? In fact, we can say it probably is slightly larger than 2. Okay, so let me draw a picture of what has happened. We have the graph of, we're talking about the graph of a function y equals square root of x, which is not a simple function, as simple as it seems. Why not? Because we don't really know what square root is. What's the meaning of the square root? Where does it come from? So I mean, there's a button on a calculator, but really, where that button comes from? It comes from some idea of what where square roots come from, and where they appear, and they appear as the inverse function of the square. So it is the inverse. Square root of 4.1 is such an x that x squared is equal to 4.1. So that is the understanding, our understanding of where our understanding of square roots comes from. It is the inverse. So if we have a quadratic equation and we're solving it, inevitably we're going to have a square root there. Okay, and so, but on the other hand, what is the square root? It is what appears in a quadratic equation. There is no other way to deal with it. That's the origin of the square root. The same thing. What is the meaning of arc sine? Well, we have a sine, and then if we want the inverse, then the arc sine will be the inverse of sine. Okay, where does the logarithm come from? Well, we are solving say exponential functions, maybe compound interest, and we need the inverse to solve an equation. The inverse of the exponential function is a logarithm. Okay, so all of these functions are come as inverses, so which means that they come with no specific way how to compute them. So look at this, what's in the box. It simply says that we gotta find that number such that when we square it is equal to 4.1. There is no algorithm for finding it other than push a button. Okay, so we certainly could push a button, but then the question becomes, what does the calculator do when we push the button? And so that's what we're trying to figure out. In a way, it does exactly what we just did, so it approximates. There are sometimes there's exact value of the function, such as square root of 4 is equal to 2, but beyond that, there got to be an algorithm to approximate that answer. So in other words, how to go like this. So if this is my 4, then I know that I'm gonna end up under this function at 2. If I start with 4.1, that's what we just assumed, that if I start with 4.1, then well, let's ignore the difference. If the actual answer is here somewhere. So this is square root of 4.1 is here, but we decide to ignore it and just go straight like this. Okay, so for 4.1 we go straight to 2. That's an approximation, and this is our error right here. The error of the approximation. The idea is this linear approximation, the idea all applicable to all functions that we cannot compute by hand, so we have to find some other ways to do it. Either for us, if we don't have a calculator, or if we are designing a calculator, we have to, or any kind of computer program, we have to explain to it how to carry it out. Okay, so well, that's what we do. This is the best bet, but as you can see, it does not require any calculus, and calculus helps us with to do better. We can do better than 2. We closer, so that they make that error smaller. And the idea is, rather than what has happened here is, in the first approach, this best bet, as I put it, what we did is we replaced y equals square root of x with y equal 2. So one complicated function was square root of x. We only know a few values of that function on the graph, so we replace it with one of those points. So square root is known for some value. So for example, square root of 0 is 0. Square root of 1 is 1 here somewhere. Okay, so some of the values are known and known exactly, and the square root of 4 is 2. Square root of 9 is 3, and so on. Okay, so a few values are known. Okay, so which means that if we know that my value is close to 4, I will pick the answer to be 2. When my number is close to 1, say maybe I have a number here, say 0.99. If I have 0.99, what my estimate of the square root will be 1 again. Okay, and so on. But it means that we ignore whatever is happening in between. And that's why we get some kind of error. So the idea is, so that's the idea on the lowest level. The idea is replace y equals square root of x with what is a better approximation of the graph than a horizontal line. So look at it. I replace it with y equal 2. This is a horizontal line. You can also see it that over here in this is the horizontal line that I'm talking about. This one. Okay, y equal 2. So the purple line is our curve. The orange line is y equal 2, which is a replacement. As you can see, it's very crude, and it guarantees that you have an error over there. So there's a better way to do it. What is the better approximation of the curve than a horizontal line? What?
Tangent line.
The tangent line. The tangent line, that's right. So with the tangent line through that particular point that we care about, and that is the point is 4, 2. So there's a graph to begin with. We don't know a lot about it, but we do know that it passes through point 4.2, which means that only half of the problem is solved. We know the point for that line. Now we need the slope of that line. Okay, so the point is through this point 4.2 slope. What's the slope of the tangent line? The slope of the tangent line is how do we find the slope of the tangent line? Rise over the run, delta y over delta x, dy over delta dx, all of that. How do we find tangent lines? What does it have to do with calculus anyway? Tangent lines. That's what the whole calculus is about. It's the derivative, the value of the derivative at that point. So how should I put it? Dy dx at x equal to, yes, so the derivative of that function, y equals square root of x over here, we differentiate it at specifically at point 4, because that is the point, the only that we know. We don't really know what's happening in between these points. These are nice points where everything is known. The value of the function is known, and there's a chance that we will be able to compute also its derivative, and then we will have the tangent line. So first of all, you can see that the advantage should, I hope, be visible. So I'm talking about if I'm zooming in on that location over there. This is my line. This is my horizontal line. This is my error that is so far we have of the approximation. Okay, so this is 2, this is 4, this is 4.1, and this is the actual square root of 2. Okay, so as you can see, that purple curve is unknown. Okay, but that it's not a really good reason to actually discard it altogether, and we replaced it with the horizontal line y equal 2. The horizontal orange line, and that gave us the original approximation. We can do better, and that we replace it with the tangent line, which will look like this. This is the tangent line. The tangent line. So then, let me show you the new error. This is the error. It's not guaranteed to be better than the original, but it is certainly overall will give us a better result. So the error is the value that we derive from this analysis versus the answer that we don't know what it is. That's the trick about approximations, is that you're trying to approximate the value that you don't know, which means that when you approximate it, you don't know how close you are to the answer. So that's a challenge. But let's figure out what. Let's just carry this all the way through. So let me take the derivative. Y equals square root of x. So dy dx is 1 over 2 square root of x. Then at 2, it is. I'm sorry, it's not at 2, at 4. That certainly matters. So at 4, it is. At 4, it is 1 over 4. Okay, so then my line passing through is passing through point 4.2, 4, 2, and at the slope 1/4. Okay, so the tangent line is then y equal, what is it? Point slope form. Point slope form. So what's the answer? So point slope. What's the formula? What's the point slope form of a straight line? No, that is slope intercept form. Point slope form.
So y2 minus y1 over x2 minus x1.
Right. That's the one. So m is 1/4 followed by x minus. Well, in the right order, I will put the value of y first. So it will be 2 plus 1/4 x minus 4. Okay, 1/4 it still appears. It is still the slope, so it appears in front of x, and then the two values of x and y appear like this. Okay, point slope form again. So that is our approximation. Then, if this is our approximation, let me have this picture here somewhere. Okay, here it is. Okay, so that's what we have so far accomplished. That is the original setup of the problem. Is on the left for point 1. We're looking for the answer 4. It is very close to 4. As you can see, that's the second picture, and we replaced our graph with the horizontal line and just said, well, that's best we can do. Okay, that's the original problem. Now on the right, we instead replaced our graph with the red line. That's the tangent line. And then we proceeded from 4.1, not towards, that's the two illustrations next to each other, is how to find the value of the function, or approximate the value of the function when x is 4.1. So either you go for 4.1 to the orange line and then horizontal to the left. That is, we call the constant approximation. Okay, so that's the constant approximation. Or, and that gives me 2 over here, or I go with a linear approximation, even though both of them are lines, but this is special line is on the left. It is constant, and so I am proceeding towards that line. There is no orange line anymore, and then from that line I'm going to the left, and here's which we're going to do next, and here's slightly above 2 will be my approximation, which is better. Okay, so let's carry it out. Since we already have everything, we geometrically, once again, as I said, this justifies why we replace our curve with a straight line, because as long as we're close to that point, the two lines are indistinguishable. In fact, if you zoom in on that point over here, what's going to happen? Those two lines will merge. So the closer you are to 4, the better that approximation is. And you can see how the approximation, it's still, that idea works out with the constant function as well, the previous picture, but you can see the difference. You can see the advantage of using the line that follows not only the point, not only shares one point with the original curve, okay? These two only share one point in common, that's all. The second picture also, they share the direction too. Point and slope. These are what the two functions share. And that's why the approximation looks so much better. It looks better, and it is better. Okay, so what do we do? Well, let's now turn this into numbers. This is my approximation. This is the function. You can say, let me just use the right words. So the linear approximation of y equal square root of x. Around, that's the word we use, around x equal 4 is, so I want to emphasize now this is a function, so L of x is equal to 2 plus 1/4 x minus 4. So once again, notice that by construction, this function shares a point, the point, with square root of x, firstly, and secondly, the derivative at that point. So you certainly, when you approximate, you want the two functions to share as much as possible, and so instead of having only one point to be shared, we have a point and the derivative to share. Okay, so that's our function. So the approximation is L of 4.1. Plug it in. So we'll have 2 plus 1/4, 4.1 minus 4, and so we have 4 plus 1/4 times 0.1, which gives me 2.025. That's our approximation. Slightly larger than 2 as we predicted. How close it is to the truth, you certainly can be verified with a calculator. Let's show that it is better than our first approximation. So at least according to what we've got. So 4.1. Oops. 4.1. 4.1 square root. Okay. So according to the calculator, if you can see it, it is 2.0246. 48. I'm sorry. 248 instead of 250. Okay, so it's really very close, as you can see. So our first approximation was 2, and the difference is the error wasn't really that large. It was 2.5%, the original approximation. But this one is, the error is even smaller. It is some small parts of 1%. Okay, so it is ended up quite accurate. Okay, so that is calculus 1. Now we're not stopping here, but rather we continue on with the same idea, which is pretty much this: how to improve approximations. How do we improve approximations when once again we have no way to compute the function, and the idea is share more. So how to improve the approximations. So the answer is share, or rather build a function that shares more things with the original than what we've got. So what else can we share? A point, the derivative. What else can we share? Well, so number 1 is the value. The value at 4 is the same. Then number 2 is the value of the derivative. So the value of the function of the two functions is the same. The value of the derivatives is the same at 4. What's the next? The value of the function, the value of the derivative, what's next in this hierarchy? The function, its derivative, what's next?
Antiderivative?
No, you're going in the opposite direction. Even though, I don't know, maybe, I never thought about it. Maybe there's a way to use it. But no, what's the next after the derivative? The next is the second derivative. Okay, so we want to also share the value of the second derivative. Okay, so then what is going to be the approximation? If you think about it, there's really, it's not going to work this way anymore, because our approximation is, what we have done best is a linear approximation, and it is a linear function to begin with. What's the second derivative of a linear function? L double prime of x. What is it? The formula is right here. So what's the derivative of a linear function?
It's the horizontal line.
No, that's the first derivative. So it will be a derivative of L of x. L prime of x is 1/4, right? So the second derivative is 0. Okay. So as you can see, it doesn't matter. Doesn't matter what the function we're starting with. Its linear approximation will be a linear function. It always will have the second derivative equal to 0. So we cannot. It cannot happen. This cannot happen with the same function because, well, the derivative will be always equal to 0. So you cannot make them share. So what do we do if linear functions are not good enough? Which way do we go? So, try what? What's the next in the hierarchy? Constant function, remember the first approximation was constant. The next approximation is linear. What's the next? Quadratic. Okay, so try quadratic. The quadratic ones will have, it is the simplest kind of function that has the second derivative not necessarily equal to 0. So they're constant. It has all derivatives equal to 0. Then you have the linear function, which is has a non-zero slope, but the first derivative non-zero, but the rest are zeros. And then quadratic are good. The third derivative will be equal to 0, but the second is not necessarily. Okay. So let me, before going into specifics, let me give you another illustration here of what I'm talking about. Here it is. As you can see, I here have all the things that we have done, 2 steps, and then the third step. So this is the first step, the graph, and what am I doing here? I'm looking at all possible constant approximations. So on the left, look at it. I have all constant functions, and I pick the best one. Right? Which one is the best of all the constant functions? The one that passes through the point. Right? So that's T naught. That is the constant function that we pick as our best approximation on at that level. Okay, then we progress to linear functions. Okay, with this. So once again, we're looking at all linear functions that pass through that point, and we want to pick the best one. Which one do we pick? We pick the tangent one. Look, you can compare. You can look at the rest of those lines, and they are no good in comparison to the tangent line. One and only one line for differentiable functions, that is, that would approximate our function well. Okay, and so that's T1. And then the next step, what happens is we are picking quadratic approximation, quadratic functions. All quadratic functions, that was this picture shows. All quadratic functions, what do they have in common? They pass through the same point, and they have the same second derivative. I'm sorry. Pass through this point and have the same first derivative. So all of these quadratic functions are tangent to my curve. Okay? They are tangent to my curve, and once again I pick one that is the best, and it turns out it is the one that has the second derivative the same as the original function. Okay, it's much less visual than the previous picture, but you can probably guess that indeed you do not want to deviate too far out of all these possibilities. If you look at the green one, it runs away pretty quickly from our function, even though all of these graphs are tangent to my curve. Clearly the green one runs away too quickly. The blue one runs away too quickly. The bottom one, the brown one, runs away too quickly, and everything that is in between is better. Okay, so it turns out there is best quadratic approximation, and it is the one that shares the second derivative. Okay, so what does so that's roughly how it is done with how calculators do it. So let's carry out this plan from scratch. Okay, so from scratch meaning from starting with constant. So best constant approximation. because we start with the simplest case, but then we see the analogy, the pattern that we're gonna follow to high dimensions. We're not gonna stop with the quadratic either. So best constant approximation. So f is continuous at x equal a to begin with. Okay, and suppose, how about I call it C? C of x is equal to k is any constant approximation of f. So constant approximation meaning any constant function, the one that we just saw on the picture. So in the very beginning here. So this is where we are. We're looking at all the possible constant approximations of the functions, and then these are approximations that do not take into account the location, right? So why would I pick the red one? Clearly, it has nothing to do with our function at that location. We're interested in one location. We're trying to compute the square root of 4.1. So that is where we are. So we do not ignore the rest of it. We ignore the rest of the possibilities. So then this is how it works out. The limit f of x minus c of x is equal to 0. That's what we're after. If and only if k is equal to f of a. So as you can see, this is the criterion of what we want to see. So you have a constant function, and you take the difference between that function. Well, we have too many functions right now. We're picking the one of them. So the key word is here, best. So we are looking at all constant approximation. We want to pick the best one, and how do we determine what is that we want, and what's in green is what we want. We want the limit as x approaches 0, as x approaches a, of these two functions to converge to 0. Okay, so exactly what you see over here. None of the other properties, none of the rest of the functions satisfy that property, and then turns out that that's the proof that we almost have demonstrated, that the function that has to, assuming that the function is continuous, then we could pick that constant approximation to be equal to the value of the function. Okay, so that is there are really not too many choices, and that picture is certainly tells you that tells the whole story. Okay, there are no other choices for choosing the straight line that would have a limit equal to 0. So what I'm looking at is at that limit that you saw. It is these values. As we approach a over here, then what's happening to the difference between two functions, and the answer is should be 0. Okay, so and then this is the result right here. Okay, so I'm not gonna prove that, but let's do the next one, best linear approximation. Okay, best linear approximation. This time, as you remember, we gotta require f to be differentiable. So the approximation only can be as good as the derivatives. So if the function is not continuous, it cannot be approximated not well by a constant function. If the function is not differentiable, that it cannot be well approximated by a linear function. Okay, so that's the thing about it. Remember, the zooming in property of a differentiable function is that the graph becomes straight. That's differentiability. If you don't have that, you cannot have a decent approximation by a straight line. Okay, so this is once again we continue the same way, and we suppose that we have a linear approximation, any linear approximation. So L of x is equal to f of a plus mx minus a. Okay, so what this formula tells us is that the value is fixed, the value is the same, just like in this picture, the second part right here. So we are looking at, let me try to align these. So we're looking at these straight lines, and then we start with the assumption that they already pass through our point. So the work that we did in the first stage, we recycle it. So we do not try to find the graph somewhere located elsewhere from that point of interest. We do pick only the straight lines that pass through that point, and then we so it's like a first test number one, and suppose they all have passed, as you can see, and now we're looking at the one that has the best slope. So then m is variable. See this m over here, this is variable. Those slopes you just saw on the picture, they vary, and we got to pick the best one. Okay, how do we pick what is the best one? And turns out we have a similar limit. It is just harsher limit that we require. Not only f of x minus this function is going to 0, but in fact it is divided by x minus a. Okay, so that is. So once again, this is how we understand best. And as you can see, the standard of best has increased from the first result to the second. So not only the difference going towards 0, but in fact it goes to 0 per distance to point A, which means that it is going towards 0 faster. Okay, and if and only if the answer turns out, we already know the answer is that the derivative is the same. So f prime is equal to m, or m is equal to f prime of a. Okay, and then we continue in the same fashion. So best quadratic approximation. So now this is f is twice differentiable. And now we want to look at a quadratic function, which is once again we recycle the results that we have had. So it has to pass through the point. So it will be f of a here. It has that's the constant part of our quadratic function. Then it has a linear part that also we know what it is. It is m. It's not m. It is in fact the derivative, f prime of a x minus a. And the only part that remains is the quadratic part, p x minus a, and that squared. Okay, and this one is to be determined. Okay, so that's our quadratic polynomial with some parts of it already have been determined. It passes through the point and has the same slope. Okay, so as you can see, it shares a point and shares the derivative. Okay, so we'll talk about that next time.